so continuing into lesson 26, just to review what we talked about last Thursday and Friday together with regard to our derivatives. On Thursday, we discussed the derivative of e to the x. Amelia, what did we learn about the derivative of e to the x? It is the same thing. It is e to the x. That is one of the functions that we have in calculus where the derivative is the same as the original function. On Friday, we talked about the derivative of something attached to the e to the x, and that's our logarithm, or the natural logarithm question. Colin, do you remember what was the derivative of ln x?
It was 1 over x.
Very good. It was the reciprocal. It was 1 over x. Now, we did talk about a little bit on Friday with regard to that logarithm question. Do you remember, Josiah, what kind of numbers can be the only numbers behind a logarithm? Positive numbers. So we had put in those absolute value bars behind our logarithm question, and that would ensure that what I'm going to take the logarithm of was going to be a positive number. You can do a logarithm with just x, but then you got to make sure that the x is a positive number. You can do the logarithm when it says negative x, but then those x's had to be negative, because negative x would go to positive x. So what we're just looking at is the absolute value bar, and that ensures that everything is going to go to positive in our question. Today we're looking at two more derivatives together about our sine and our cosine graphs. Now, before we look at a couple things in our textbook here on page 148, we're going to notice something about the angles that they're going to give us in these questions. All of the angles that we're going to be talking about on the sine and cosine graphs, because the angle would be the x on this question. That's what you put behind a sine or a cosine function. Is the sine of 30 degrees, is the cosine of pi over 2. When we're talking about angles that are measured in radians, a majority of those angles are given in terms of pi. Do you guys remember from last year, even in Algebra 2, what degree measurement does pi represent? 180 degrees. That's how we've done the questions before. If it said pi, we replace that with 180 degrees. I mean, you can technically do that on these questions, but everything that they're going to talk about for the derivatives for sine and cosine would always be in terms of our radian measurement. Let's go ahead and look at our first one with regard to our sine function. And this is what I'm going to have you see if we can figure out together on the graphs on the bottom of page 148. Right, so if you look on page 148 for me, for the left two graphs, so the two that are on top of each other on the left-hand side of the picture. The top graph, and there's a lot of lines, a lot of information in the picture, so let's see if we can break this down a little bit here. That top left-hand graph represents your positive sine function. Remember a couple of characteristics about sine. It had to start at the origin, which I do see there on this top left-hand picture. That graph begins at the origin. It does hit that. Why is this an example of a positive sine graph and not a negative sine graph? Because it went up from the origin. In just a second, on the bottom right-hand corner, we'll see the negative sine graph. For the negative sine graph, again, it does hit at the origin, but then this one went down from the origin. Let's look at the graph right below it. Now we're going to see if we can make some comparisons here. The graph below it says y equals cosine x, or cosine theta. What was the main difference between a sine graph and a cosine graph? It doesn't start at the origin. Where does this graph start for that bottom left-hand picture? Where does cosine theta start? It starts at positive 1. Why does it start at positive 1 and not negative 1? Because it's the positive cosine graph. If it would have said negative cosine theta, which we don't see a picture of that here, but if it does say negative cosine theta, then it would start down at negative 1, and then it would go up from there in our question. Now we know when we're talking about derivatives, the derivative is the same thing as finding the slope of the tangent line. And this is where we're going to see if we can recognize some things in our picture. If you will take a look at the top left-hand graph where we have our sine function, and let's evaluate pi over 2. Okay? So everyone see that pi over 2 on the top left-hand picture. If you will follow the dotted line up, there's that dot on the top, and then they drew a horizontal line in for your tangent line. Everyone see where I'm referring to, okay? What is the slope of a horizontal line in any kind of question? It is 0. Remember, our definition of slope is rise over run. It doesn't rise, so the rise is 0, but it does run, so it's 0 divided by something is still 0 on your question. Okay, now here's the connection we're going to see if we can make. Follow that dotted line down to the graph that's below it, which is the cosine function. Where does the cosine function hit the x-axis at that same angle of pi over 2? It's at 0. Okay? Did the sine function hit the x-axis at 0 at pi over 2? No. Okay, it's up there at the value of 1. Okay, but what did we notice about the slope at the pi over 2? The slope was 0. As I follow that down to the cosine function, I notice that the cosine function hits the x-axis at 0. There's a relationship that we're going to notice here in just a second. Let's move over a little bit further on the graph to where it's not labeled in the picture, but it's at the bottom of the hill, where again you see a horizontal line. Everyone see the picture where I'm referring to on the bottom of the hill, where again there's a horizontal line. What is the slope of a horizontal line? It is 0. Follow your dotted line down to the cosine function. Where does the cosine function hit the x-axis at that exact same location? It hits at 0. So the slope for the sine function was a 0. The cosine function actually has a value of 0 at that exact same angle in our picture. Okay, everyone see what I'm trying to refer to so far? We're going to see if we can make a connection with this in just a second. Let's look at one more together. If you will look at it, it's the last dotted line that we have in that picture, so it's the last dot that they gave you where the 2 pi is located. Notice that that graph, that line, that tangent line is going up. Because the tangent line is going up, that means the slope is going to be a positive number, based on the definition of rise over run. Now, in order to get to the slope of that tangent line, it had to go up 1 space, so it could get to the number 1, then it goes over 1 space as well on the x-axis. What is the slope if it says 1 over 1? It's just 1. Okay? Follow the dotted line down to the cosine graph. What is the value of the cosine graph at the angle 2 pi? It is 1. Okay, so what have we just noted? The slopes, which is the derivative that we see in the sine function, matches with the regular answer of a cosine function. Okay, so if you will mark this down for me, the slopes that we saw on that top left-hand graph. So what's the slope? Is the derivative. The derivatives that we noticed for the sine function were the exact same values for the regular cosine graph in our question. Okay, so again, we're just, in case you want to put this in your notes, we noticed that off the graph on page 148, so you can go back and see where we got that from. Okay, so again, what does this tell me? What am I calculating when I'm doing the slope of the tangent line? So what vocabulary word means the slope of the tangent line? You saw on the screen there at the top of the page. The derivative, okay? The derivative is the slope of the tangent line. So the slope of my sine function, which is the derivative of the sine function, equals the cosine function that we have. So this is our next derivative that we're looking at here, the derivative of your sine function. The derivative of sine is cosine. Whatever we looked at for the slope on the slope on the sine graph was the same regular answer when it came to our cosine graph in our question. So that's another way to say it in our derivative notation. The derivative with respect to x of sine is cosine. So if my question says find the derivative of sine 30 degrees, what is that wanting me to do? My answer would be the cosine of 30 degrees. Why is that the case? Because those two values matched. The derivative is the slope. We just noted 3 different slopes on our sine graph. Those slopes match the actual answer that we had from the regular cosine picture on our book. Okay, do you guys understand that? Are we a little bit fuzzy on that? Or are you just going to believe that what I'm telling you is correct? So the slopes that we saw match the sine graph. All right, let's see if we can do the second one when it comes to our cosine function. Let's see if we can do it the same way. Then we'll write it down on the board together. All right, so let's look at the graphs that are on the right of page 148. Okay, on the top right-hand section, they again drew out the cosine function. I knew it's the cosine function because it starts up at 1, then it goes down, and then back up in the question. The bottom right-hand graph that they drew on page 148 is negative sine x, or negative sine theta. Why is that bottom right-hand graph negative sine theta and not just sine theta? Because it went down from the origin. I know that it is a sine graph because it does hit right at the origin, but this one goes down from the origin as opposed to the top left-hand graph that we saw, which went up from the origin. Let's see if we can do some same things in our picture here. If you will go to the value of pi that you see on the top part of your graph. Okay, so the top right-hand graph, find the angle of pi, follow it down to the curve, you're at the bottom of the hill. At the bottom of that hill, they drew in a tangent line because it just touches that cosine curve once. Well, it's a horizontal line. What is the slope of a horizontal line? 0. Okay, follow the dotted line down to the bottom graph. What do we notice is the value of negative sine theta at pi? It is 0. So again, there's a connection. Let's look at just one more together about this cosine graph. Go to the next angle over, which is 3 pi over 2. On the cosine graph, we have a dot, and that dot is right on the x-axis. But for the top graph, I'm looking at the slopes because I'm trying to figure out the derivative. What is the slope for the cosine function at 3 pi over 2? So notice that line's going up. It is 1. Follow it down to the negative sine graph. What is the value of the negative sine graph at 3 pi over 2? Okay, so follow that dotted line down. Where is the negative sine graph at the angle 3 pi over 2? It is 1. So the slope that I had on the cosine function, the slope, which is the derivative, was 1. As I follow it down to the negative sine graph, I notice the negative sine graph also has an answer of 1 at that exact same angle. So what we're going to notice for our cosine graph, the cosine graph for its slope, again, slope is derivative, and that's where we're focused on. The slope equals the value of negative sine for all of those different values of x. Okay, so again, it was just negative sine because we were looking at the negative sine graph. Again, it started at the origin and went down from there in our picture. So far we've noticed the sine graph, the derivative of sine equals the cosine. It's the exact same value for the derivative of sine and the answer for cosine. For our cosine functions, again, it's on page 148 if you need to make a note in your notebook here. What do we notice for the derivative of cosine? It is negative sine x. So again, if the question says find the derivative of cosine pi over 2. So again, normally those are in radian measurements. The last example I said was degree. I mean, technically it doesn't matter, but usually they're in radians. So if it said the derivative of cosine pi over 2, to calculate that derivative, I would just need to answer negative sine pi over 2. I would be looking at it in terms of a sine function in our question. All right, so sine goes with cosine, but cosine goes with the opposite. So it goes with negative sine in our question. Let's see how we're going to use these on 2 final questions this morning where we're actually going to calculate the derivative. So if you go ahead and mark down this first question for me, we'll do 2 of these, and I have some out of the textbook that we'll try together as well. Okay, so our job is to find the derivative. Again, as we're getting into these derivative questions, it's not once necessarily that we can use that product rule where we drop down our exponent and then subtract 1. These are ones that we kind of have to start memorizing so I can easily replace them into the question. So our function is y, so I'm going to say the derivative of y with respect to x. Again, that bottom part is because the x is the variable of our question. All right, so the first thing I run into, I have 3 different pieces. We'll do each one individually. It says 3 sine x. So my 3 drops right down. That doesn't affect anything about our derivative. I run into the sine function. What did we just notice was true about the derivative of sine? Josiah? It is cosine. So I'm going to go ahead and fill in cosine x in our question. Again, that came from the first 2 graphs. Whatever I had from the slope of the sine function was the answer from the cosine function. I move to the second part of our function, and it says minus cosine x. Well, again, I need to find the derivative of cosine x. Anna, what did we just notice about our derivative for cosine x? It is negative sine. Now, our question up here says minus cosine. That derivative is negative, so minus and negative is going to switch this over to a plus in our question, and then we're going to fill in sine x on our question. Again, how did that happen? The derivative of cosine was negative sine x. Minus and negative goes to positive. The last part of this is what we talked about last week. Colin, what is the derivative of 2e to the x? So this was one of our special ones we talked about last week.
Oh, it's 2e to the x.
Is 2e to the x. When we had that e function, our natural function, the derivative matched the exact problem, and that is my answer for the derivative. In our lesson that's coming up here, lesson 27, that we're going to get to on Wednesday, once we calculate the derivative, they're going to give us something to put into that derivative for the x. So we would have to be putting some angles because we have our cosine and our sine function on this question. Before we do our second example today, any questions on how we just correctly did sine and cosine on the first one? All right, let's finish up with our last problem for today then. Our function, y equals negative 3 cosine x plus 3 ln x minus 2 sine x. Again, our job is to calculate the derivative. All 3 of these pieces are 3 special kinds of derivatives. I cannot just use my product rule. So our derivative of our function y with respect to x. All right, so the first thing we run into is negative 3 cosine x. The negative 3 does not affect the derivative. It's just going to get multiplied by something in just a second. Let's look at cosine x. Amelia, what did we just notice is true about the derivative of cosine x?
It's negative sine.
Okay, so what am I going to write down for the first part of my answer, Amelia?
Negative 3 times negative sine.
Very good. So the negative 3 drops right down. The derivative of cosine is negative sine x. All right, let's move to the second piece of our question, 3 ln x. Again, the 3 in the front is just going to be multiplied by whatever we come up with for the derivative. Josiah, what was the derivative of ln x? That was our one from Friday last week.
Was it e to the x or
So,
I don't know.
okay, do you see that in your list? It was from Friday's part of the lesson, the derivative of ln x. So the first one was our e to the x, where the derivative was also e to the x. Do you see anything there about ln x?
I know it's defined only for positive values.
Okay. What do you have for the positive values, or do you not have anything there? Oh, there it is. Right there. So there's your derivative.
Oh, and the 1 over x.
1 over, so the derivative of our natural logarithm function was 1 over x. Okay, the last part of our question, minus 2 sine x. So I'll drop down that minus 2. Colin, what have we learned today about the derivative of sine x?
Cosine.
It is cosine x. So those two things are exactly the same because the slopes that we saw in sine was the answer from the cosine function. We just neaten up some of the work here. So negative 3 times negative sine x is positive 3 sine x. 3 times 1 over x is 3 over x. And that last part of the question cannot be simplified. And there is our final answer for our derivative function. Alright, so again, the derivative is giving us the slope. To help us with our sine and cosine, we have to look at the slopes of the actual graphs. We noticed that the slope of one graph was the answer out of the other graph. Okay, so just make sure we understand our 4 special derivatives that we've learned about in lesson 26. Amelia, what was the derivative of e to the x?
E to the x.
E to the x. Colin, what was the derivative of ln x?
1 over x.
1 over x. Anna, what is the derivative of sine x?
Cosine.
Cosine x. And Josiah, what is the derivative of cosine x?
Negative sine.
Negative sine x. Okay, before we look at what our assignment is from our textbook today, any questions on the derivatives that we've looked at from lesson 26?